screen. So as I said, the countdown started. We have 2 classes for today and for tomorrow, and those will be the last classes. And so next week it will be a break for you from concrete. I don't want you to get disconnected. Make sure that you have some time to study concrete, because I guess concrete is your first final exam. Okay, so please study. If you have any question, I will make myself available for again, as usual, reasonable hours, not midnight. If you have any question. And I think also what I will do in surveying is I will do the first class of next week, but not not the last one, not the Friday. So the Friday will be off for surveying. Okay, and hopefully this is another good news for you. What else I want to say before we discuss today? Anyway, if I remember, I will just, I will just let you know. Now, today is the last chapter of our course, which focuses on foundation design. Foundation design. And let me just remind you of foundation. So look at the name, foundation. Even foundation, we use it for any, doesn't have to be with a building, in life, foundation. So it looks like foundation is something very important, because every time we refer to a good basis, we say foundation. And this is exactly what's happening for the building. So the foundation is the lowest portion of your building. Okay, it takes the load from all the upper elements, beams and columns, and simply safely transfer the load into the soil. It's very important topic. The failure of the foundation, I bet you it will fail the entire building. Even sometimes when the foundation system is not built or designed properly, it causes catastrophic, like event for your building. Okay, if you chose not really the best foundation system, let's say you're supposed to go with piles, but you never did piles, and then you did like just a shallow foundation, as we speak, as we discussed today, your structure maybe will have significant settlement and significant deformation and lots of cracks, and probably the building will have to be demolished. Okay, if not collapse. So really the function of the footing is to spread, and you can see on my screen that I highlighted the word spread with red, okay, because really that's what does. It spreads the load that comes from almost a point load into a reasonable a reasonable level of stress into the soil. Okay, here is the point. We build of concrete, of steel, or whatever material, all of them, they are stronger than soil, stronger than soil. And simply what happened is, if you just put the column straight into the soil, can you imagine what's going to happen? If I simply add column on top of the soil without any footing, can you guess what happens?
It will collapse. It will collapse.
It will simply sink. And I'll, like I'm saying, like just my finger. So look at my finger. Okay, so my finger is here, so that's the column. I put the column on top of the soil. The stress is very high. It comes on a very small area, and if you apply the same level of stress, like let's say 25 MPa or 30 MPa for concrete on your soil cannot take this big stress. So the function of the foundation is to spread, reduce the level of stress, because simply you increase the area of contact between the concrete element and the soil. When we increase the area with the same load, what happened to the stress? When the load is constant, but we increase the area, what happened to the stress?
It spreads out over a bigger
It
area.
spreads out and decreases. Okay, and that's exactly what the footing does. Actually, there are a couple of mechanisms which is really beyond the discussion in our class here. So the way that footing, a foundation will transfer the load into the soil, As far as I know, I'm not sure if there is any more because I'm not really geotechnical engineer, but as far as I know, there are two techniques that the foundation will transfer the load safely into the soil. Something called load bearing. So the element will bear on top of the soil, and other mechanism is called skin friction. Okay, we're not going to cover skin friction. Skin friction is used in piles, and piles are outside the scope of this course. Now, here is something very important, and it will be more clear as we go through the class today. The foundation design is a cooperation between two different disciplines. It's not only structural, it is not only geotechnical, it is a combination, or I would say cooperation between the knowledge from structural engineering and from geotechnical engineering. However, I want to mention something, and let's be clear. Who decides that the foundation system? What do you think? Is it the structural engineer who decides and say, you know what, I will do piles, or I will do like shallow foundation, all those kind of choices?
The
The
geotechnical.
geotechnical.
Exactly. So the geotechnical engineer, I bet you, like, you got probably a course or two with Brian or maybe Ramin, and you know that the one decides for the foundation system is the geotechnical engineer. There will be a geotechnical investigation where soil samples will be collected and soil tests will be done. And then from all this investigation, the geotechnical engineer will come up with lots of recommendation, among which okay, hey, design engineer, the best system for your area here is piles, or raft footing, or a spread footing, or whatever system the geotechnical engineer will recommend. So initially it comes from the geotechnical engineer, the system, and the structure engineer will take these recommendation and will proceed in their design. Now, when we say foundation, this word foundation, it is very, very wide topic. There are books that you can read in foundation system and foundation design. Now, mainly the foundation are classified according to the following. So some of the foundation, we call them shallow because they are very, very close to the surface of the earth. And some of them, they go deep into the earth. Okay. So I'm going to start here with the topic that we will not cover in our class, which is deep foundation. So let's be clear. Deep foundation will not be covered in our class. So when we say deep foundation, again, as far as I know, the system, it's when I say deep foundation, it is equal to the piles, and then they are used when the soil is not really strong enough. When the soil doesn't have enough bearing capacity, the soil is weak. Then what we do is we go and do piles. And so the piles, there are so other, like when it comes to piles, there are so many of them. Like I can tell you some names. There is something called end bearing piles and skin friction. And looks like here we're talking about the mechanism of how the load will transfer from the pile into the soil, either by the skin friction or the skin along the surface of the pile to the soil, or same as the other footing, it goes by end bearing. End bearing, it means, let's say the top layer of the soil is bad, so then I dig down until I find a good layer of soil that can bear the load. Also, from the perspective on how we build them, we have something called bored piles and driven piles. And probably you guys know what does it mean, huh? Bored is we get a rig machine that drills a hole into the, or drill the pile. So we get a machine or a rig that drills a hole into the ground. Then we drop the cage, and then we simply pour concrete. The other kind is called the driven, and the driven piles are, is kind of a ready element. It can be steel or concrete or even wood that you hit the pile hard on the top and you drive the pile into the soil. Okay. Anyway, again, that's a big topic. I'm not expert by any means in pile design, because I'll tell you something which will surprise you. The structure engineer does not design piles. Okay, so if you have even, let's say the structure engineer recommends you that use piles, we do not. As a structure engineer, we do not design piles. The only thing we do for piles is we estimate the load on top of each pile, and then we show the loads onto our drawing. And who designed the pile? What do you think? So structure engineer, like an engineer designing a building, and the geotechnical engineer say use piles. All I do is I find the load on the pile, and then who designs the pile? It is not a structure engineer. It is the pile contractor. So the pile contractor or the piling company, typically they have their own engineer who designed the pile. We only review them. So they come back, we review them, that they take the loads, but they sign them off. So the piling company, they send us shop drawing for the piles, and those shop drawing, they are unlike any other shop drawing. They are stamped with an engineer because they take liability of the design. We do not design piles. Anyway, probably you learn about pile design in other classes, like probably with Brian Bax or I think. Now, what are we going to cover in our class? So the other classification of pile is something called shallow foundation. It means a system of foundation that is kind of very close to the surface of the earth. And we have many of them. Here I listed 5 of them. So there is something called spread footing, and sometimes we call it bat footing. And we have a straight footing, we have combined footing, and trap footing, and then raft slash mat foundation. In our class here, you can see we have only 4 hours left, and we are going to only cover the one that I highlighted in red. So we are going to cover in our class something called spread footing and something called strap footing. And the names, you can see the names are very, very close, even strap footing. So I don't want you to get confused. I'll show you the difference later on. But we don't have time to cover the combined footing or the strap footing or the mat foundation. I mean, I'm going to show you the what do we mean here. So this is kind of a graphics here that shows you the each one, what does it mean. So here we go. This one here is our spread footing, and this one is a strip footing. And those are the ones that we will cover in our class. So this one is called combined, and this one is called strap footing, and those will not be covered in our class. Really, at this point of time, I want you to look at the A and like picture A and picture B and tell me what is the main difference, just without even learning about them. Do you see any difference between a spread footing and strip footing?
One
Yes.
supports a column, one supports a wall.
Exactly. Thank you so much. Who said that?
It's me.
Thank you, Martin. So look at this. Exactly. So the spread footing or the bat footing, it supports a column. So it's kind of a point load going onto the footing. And this one is not a column. This element is a wall, and the wall is extended in this direction. Okay. Those will be covered, and I will show you today. We're going to cover 100% of this footing here. I'll give you a numerical example on how to design a strip footing today. Now, here is a picture of a raft foundation, and you can tell that it's very serious. Look at how the amount of reinforcement in this raft footing, and you will see how serious, and that's why it is so serious. There is like a forest of reinforcement, and I don't know if you're surprised. The mat footing or raft footing, it is a slab, but the slab rests on the soil. But why it is different from any other slab? Because if you have a building that is 48 floors, every slab on every floor, it carries only the load from this floor. How about this slab? This slab, it carries the load from all the floors. Okay, I'm not sure if you can imagine that. So you have a slab at the very, very bottom of your building, and simply all the columns are pushing on top of this slab, taking the loads of the entire building to the soil. And so the load that this slab is supposed to support is simply the load of the entire building, as simple as that. And that's why it is very thick. It can be 1.5 meter, it can be 1 meter, sometimes it can be 5.5 meter. So I heard about some systems, I think Burj Khalifa in Dubai, which is the highest building in the world so far. I think the raft slab is crazy thick. I heard some numbers, not 100% sure. So please take my number as like a fact, but it's like about 4 to 5 meter thick. Can you imagine? 4 to 5 meter thick, and it has lots of forest of rebar. Anyway, it's outside the discussion of our class, and let's move on to see some other interesting topic that we need to prepare you before we design our footings. Number one, I know that you heard about soil bearing stress in other classes. Soil bearing stress in other classes in geotechnical. So the soil, when we apply a load into the soil reacts to our load by a bearing pressure, and because we have sigma y equal to 0, it means the soil will have to provide a reaction equal to the applied force, which means if I apply a load like so on the column, so the soil will have to react by a stress. And if you take the stress multiplied by the contact area between the footing and the soil, those they must balance. So if I have here a force called P, which is the load, so simply the soil will react with the pressure called Q, and if the area here is equal to A, simply if you multiply A times Q, then you get it's supposed to be equal to the P. Okay. Now the stress distribution under the footing, you see on my screen here 3 different picture. One, which is A, and then B, and the C. Guess what? The one on the far left, it is not real. It is not going to happen. The soil, when it reacts to the load, stress distribution it looks like either B or C. It depends on the type of the soil. Not only the type of the soil, it depends on the stiffness of your footing. And I know, you know what, this is not an easy discussion. I want you to think about the soil as springs. Okay, so we have here elastic springs, and I think at some point of our course we talk about stiffness. Okay, so I would say straight under the column, probably there will be more pressure straight under the column. And as you go away from the column, because this will cantilever out, so because it cantilever out and it has, it flexes a little bit up, because it flexes a little bit up, what happens is you get less stress as you approach the tip of your footing. Does it make sense?
Yes, that makes sense.
Yeah.
Okay, so but again, this discussion is not pure. I mean, what happens if this footing is so thick and it's very, very strong? It means it's very stiff. If this footing here is very stiff, guess what? We will see this kind of a stress, because this guy or this footing here is very stiff, and simply it doesn't bend up as much, and it will cause a uniform stress underside the soil. And again, it depends on the type of the soil. You know what? I will make your life simple. Although this one is the one that's going to happen, or this one, however, in our design, we typically use this one here. Because this one is not easy. How do we know the shape or the exact shape of the stress under the footing? It's kind of not easy. You have to do kind of computer model, and to model the soil as elastic springs and with a given stiffness, and you will see the real interaction between your footing and the soil. However, in our simple design, we will take a simplified approach where the stress under the soil will be uniform. Is that clear?
Yes, that's clear.
That's clear.
Okay, perfect. something, this slide, I'll tell you, this slide is even more important than anything I'm going to say today, to be honest. Although it doesn't have any design, but it has a piece of information, which is, to me, it's very, very important, okay? So in any other part of the world, you know, the geotechnical engineer will do some kind of soil, like take soil holes and mix soil holes and collect the sample, and they will understand the profile of the soil as we go down. So maybe the top is a weak soil, maybe after 1 meter we have a better soil, and maybe after 3 meters we have a different soil. So we get a profile of the soil. So in other part of the world, which the weather doesn't get very cold, really the level of the footing, which is this level here, I'm going to point out this level here, is completely dictated by what? By the soil bearing capacity. Where can we get a good soil? And we can dig down a meter, or maybe a 30 centimeter, or maybe a 1 millimeter, okay? That's the thing. Typically, it's not 1 millimeter, 100%. Will never be less than 30 centimeter, because even if you have a rock here, a rock, that the first 1 foot typically it is very weak because of the weathering of the conditions. So what happened is we typically never even use the first 1 foot, because it's very weak. But the thing is, in areas of the earth where it doesn't get so cold, the level of the footing, which is this elevation here, it is controlled by where do I have a good soil, good reliable soil. In Canada, this is not the case. In Canada, even if you have good soil very close to the surface, we cannot do that. I think by now all of you know why. And I can get some help, huh? What do you think? Why? Frost. Okay, exactly. It gets very cold here. The soil has moisture, and you guys know what happens to the water when it freezes, huh? It expands and push, and it's very, very strong. Mother Nature is very, very strong. It can give an 80 MPa pressure. 80 MPa. Do you hear it right? 80 MPa. Okay, so it can take your entire building and push the entire building up. Okay, and so that's why we need to go to a safe foundation level. So where is this level? Again, so you can tell in Canada, it's not only one factor, it is 2 factors. So in Canada here, this foundation level goes from 0.45 meter to 2.1 meter. And it depends on the climate region. By the way, so you know, and this is obvious, in Canada, there are some areas which is very, very cold, and some other areas which is not that cold. So I think somewhere in Saskatchewan, it goes to -40, -50, and it stays for -40 for a long time. In close to the mountain, we don't get this cold temperature because of the air movement, but we get lots of snow. And it's not about snow, it's about the cold, okay? So the colder it gets, that you need to dig down more and rest your footing on an area which have enough soil cover, which protects the footing from freezing, okay? So the number here is 0.45 to 2.1. And so the foundation, as I said, it depends on 2 things. Number 1 is the climate region, and also it depends if the building is heated or unheated. If the building is heated or unheated, okay? So if the building is heated, I'm going to give you the numbers in Calgary here. If the building is unheated, then we need to go to 7 feet below ground. We need 7 feet of soil cover to protect our footing. If the building is heated, then we need 1.2 meter. And the have a, like, let's say, walkout basement. If you have a walkout basement, which one do we do?
1.2.
Heated.
Yeah, we need to, if we have a walkout basement, on the walkout side, on the back of the building, probably you must have a 1.2, because a basement is always heated, and that's why we need a 1.2. I'll tell you, sometimes you will see we cannot maintain this 2.1, like 1.2. And I'll tell you an example that I have myself, I've done it in the past. So sometimes you cannot maintain 1.2 meter for a heated building. Now, what's the situation? So sometimes there is an existing house, and later on they decided to develop the basement and develop the basement as a separate suite. If you want to develop the basement as a separate, then what you have to do is you must provide a separate entrance of your house, of the house. And if you want to provide a separate entrance and the house was not originally designed to have a separate entrance, like the old style, the bungalow, then what you do? Then what you do after the building is already done, then you have to dig around the building. I'll give you an example. Let's say this is my building here, or that's the house, and let's say you want to get an entrance. So what you do is you typically dig this area to make some steps to go down. Okay, you will do some steps to go down, and you have no other choice. In elevation view, here is an elevation of the side. Okay, you will need to have a door, and so this door will be like so. Okay, and in this case, remember, stairs are going like this, huh? So the stairs will go down like this. So you can tell you're removing the soil. So which means when the building is there, then there was a soil protection. Let's say that's the grade, huh? Let's say this elevation is the grade. Okay, so you can tell if you do that. So what happens? You're removing the soil. You're removing the foundation protection. So what you have to do is you must do insulation. So you must add here a rigid insulation to simply protect the footing. If you guys remember that, or if you can visualize that, okay? So this will be here. This will be a footing, a rigid insulation to protect. And the rule is for every 1 foot we miss, we simply replace it by 1 inch of rigid insulation. So in this case, what happened is we need to provide here a 4-inch rigid insulation to protect the footing. Are you guys following?
Yeah, we're following.
Okay, so one more thing I want to emphasize is this number here is your foundation depth. And on our drawing, we say minimum. Let's be clear. We say minimum foundation depth. Does it make sense? Why we say minimum? So for example, we say 1.2 minimum on the drawing, 1.2 meter minimum. Do you know why?
That is the minimum points that you can go down.
Yeah, but this is a protection for ourselves because simply, number one, it is dictated by the frost height or the frost depth. And in addition to, we need to make sure that we have enough bearing capacity. So we say go to 1.2 meter. If you find a good soil, great. If you cannot find a good soil, what you do is you go even down more than 1.2 meter. And really, it has to do with the inspection. So the geotechnical engineer will arrive to the site, will ensure that the current, like this level, like this elevation of the soil, it has enough bearing capacity as per the design document. Okay. Something also goes around the bearing capacity of the soil, which I know this is kind of confusing. So please, if you've been sleeping from the beginning, please wake up. This is very important, huh? So when it comes to the soil bearing capacity, you guys have been with me in the class right now, and maybe you've been with Corwin now for more than like 12, 13 weeks. And you guys know, what do we do with our loads? We factor our loads. We factor our loads because we're doing ultimate limit state design. Ultimate limit state design. Would you agree? So we take our dead load, multiply by 1.25, and we add to live load, multiply by 1.5. Okay? So that's called ultimate limit state design. I would say 20 years ago or 25 years ago when I was in school, this was not the methodology for the design. So they have something called working stress design, which means we don't factor, we do not factor our loads. We just take the dead load plus live load and we add them without multiplying them by any load factor. So that's called working load. So you can see two schools. One school, which is, I think this started roughly about 20 or like 25 years ago. Actually, the transition was when I was about to graduate. So when about to graduate back in 1996, so this new methodology of the design came about, It's called ultimate limit state. But before that, there's something called the working stress method. Now, how this affect the discussion? Not very difficult. So before, when we used to design in working stress, our geotechnical engineer provides us with something called Q allowable. It tells us, you know what? Apply this allowable stress to the soil. It can take it. For example, it will tell you use a 50 kPa. So under the working load, the maximum stress will be Q allowable, let's say 50. When the ultimate limit state design method came, and I think it controls everything right now, the geotechnical engineer will start to change. Will start to see what or how much the Q factor for our soil. The thing is here, the geotechnical design did not pick up very fast as the structural design. Structural design, very quickly, they changed from working stress method to ultimate limit state method. But geotechnical design, some of the old engineers still until now, probably they give us on the report, they give us something called Q allowable, not the Q factor, okay? So really, the discussion, all you have to do is be careful, be careful. If the Q allowable is given to you and you want to size your footing, you must use the working load. If the geotechnical engineer gives you the Q factor, it means you can use the BF, which is your factored load. No matter what you use to size your footing, in our concrete design, when we try to find how many bars and what's the depth, what do we do? Do we use working stress or ultimate limit state? What do you think?
Ultimate limit state.
Okay, so I mean, if you're not clear, it's okay. In the numerical example, I will show you how this will work. Okay, so please be patient until I discuss with you the numerical example shortly after the break. Okay. Now, something you will notice, and I think you will be very happy today, because you know, you have done a lot of effort in my class, and if you know exactly what was going on in my class for the last 12 weeks, this will pay you off today. There is absolutely nothing new in the footing design, in the strip footing design. Nothing new, okay? And I will prove it for you as we go through the numerical example. But here is our strip footing. Remember, a strip footing, we have a wall. So this guy is a linear wall or linear element. So this wall, and we simply extended the strip footing under the wall. The way we design the wall as a one-way slab. So the wall is simply pushing down like so. And when the wall pushes down and the soil reacts to this with the soil pressure, guess what? This here will work as one-way slab. It levers from both sides. It can levers out from both sides. And the way we design it, we will design it as one-way slab with everything you learned in my class, same, it does not change. And if I need to remind you, the one-way slab, the way we design it is we used a 1 meter design strip. A 1 meter design strip, okay? So where is this 1 meter design strip? It is, here we go, this is my design strip, and probably I have to add here couple of few lines for you guys so you can visualize where is my design strip. So this will be the design strip, which acts like a beam. Okay, let me change the line type here because this is hidden. So this will be the 1 meter wide design strip. I need also to remind you the load comes from the wall down to the footing. It is always estimated as, for example, it will be PF. And what are the units? Will be kilo Newton per meter, per linear meter of the wall. This is unlike the column. When we estimate the load on the column, what will be the units? Any help?
Kilonewton.
Yeah, so for the column, it is a point load and is estimated to Newton. For the wall, the load is estimated as kilonewton per meter. Per meter of what? Here we go. Here is the meter. So per meter of the wall length. So this guy here is one meter. Okay, now. So in our design, the wall will have to be designed. Sorry, not the wall. The footing, the straight footing will have to be designed for two main loads, which is the shear force. So if it's just like a slab, so my slab, it has to be safe in shear, and also it will have to be safe in bending moment. One more time, the one-way slab will be, the strip footing will be designed as one-way slab, cantilevers out from both sides, and we have to make sure that this one-way slab is safe in shear and is safe also in bending, okay? And you will see here 100% similar, not similar, 100% exactly like one-way slab, okay? So do you guys remember where was the critical section in one-way slab? Did you remember when we designed a beam, okay, which is in shear, where was the critical section? And if you remember that we go from the face of our column by distance called dv, because this angle here, this angle here is about 45 degrees. 45 degrees, that's the angle of the crack. And so what happens here, really the critical section in shear, not really at the face of the support, but really at distance dv, because as we said, as the load goes down from the wall, it spreads out on an angle 45 degrees, and simply this area is very strong, and we need to make sure that the force here is simply less than the VC. Okay, so bottom line for this slide is the critical section for shear is at the face, not at the face of the wall, rather than at distance d sub v from the face of the wall. To be honest, I would give you a break here, and after we come back, we'll continue on the theory part, and then we'll give you a numerical example. So we'll give you 10 minutes a break. We'll see you back here at 8:53.